towards the center aisle. Sarah can come collect them and then hand them to Harry. With that, Leo's next. He's going to be talking about synthesizing visual specifications. Where he's, I know something about his work. Do a good job.
So, hi everyone, I'm Leo, and I'm a third year PhD student co-advised by Josh and Ansak. So, I will be talking about synthesizing visualization specifications from examples. I'm going to start with the motivation, and the motivation is something I've always talked about. It's visualizing formal models. Suppose you have a system, like a software hardware system, that you are trying to understand the behaviors of. Formal modeling allows you to provide a model, which is a logical specification of system behavior. And using tools like Alloy or other like formal methods tools, they can generate you instances, which are essentially concrete examples of the model. These instances can then be visualized into some sort of visual representations. So now, why would people want to visualize their instances? They want to visualize their instances because the visual representations, they help people understand the concrete semantic meanings behind the instances. And the instances hopefully captures the behavior of the model, and the model captures the behaviors of the underlying system. So the goal is that the effective visualizations, they should help stakeholders understand the behaviors of the system that are being modeled. So what do such representations look like? If we ask tools like formal methods tools to generate you a specification, generate you a visualization, here they are. Here they are. The one on the left is a Daniel philosopher's problem model and its visualized instance. And the one on the right is the railway systems model and its instance that's being visualized. And as we may see, these visualizations are not really effective in helping stakeholders understand system behaviors. And that's because they try to use the same visual style across a variety of domains, the same visual style being boxes and arrows. And this is not something that stakeholders find very intuitive. Our prior study have expressed that the stakeholders want to customize their visualizations to match how the domain is usually visualized in their industry. They also want to customize how things like relationships are being visualized geometrically, for example. So let me show you some of these custom visualizations that people have made. The first, for the Daniel philosopher's problem, you can see that there are some important customizations that the stakeholders actually care about. In particular, that some of the nodes are laid out in a circular layout, just like how a stakeholder would think about the problem domain. For the railway systems model, this is one of the custom visualizations that they have come up with. There are some important layouts that some shape contain other shapes. That the shapes are some shapes are laid out in a linear fashion, like from left to right, and that some other shapes are closer to the shapes that they are related to. There are plenty of prior works that enable this type of custom layouts. For example, our prior work Panloy can generate visualizations like this for the railway systems model, but it requires users to write a custom style program, which spells out that, for example, if some relationship exists between some elements of the instance, then some sort of geometric relationship must hold between the shapes of those entities. Tools like Sterling can also generate the visualizations like this for the Daniel philosopher's problem, but it requires users to write a full-fledged D3 program in JavaScript. You have tools like Cop and Drag, which requires users to write a program in a domain-specific language to generate something like that. In general, if we summarize what these custom visualizations tools do, it's that they require human-written visualization specifications that spell out detailed instructions on how the nodes, how the objects should be laid out visually. The problem is that such visualization specifications can be difficult to write, and this is something that prior work and other stakeholders have complained about, that it can be very time-consuming to get the right visualization specification. Since writing visualization specifications are hard, a question we are asking is, can we approach this another way? instead of using visualization specifications to make a diagram, can we invert the process and use some sort of user-provided examples to infer a good visualization specification? In short, given a model and some example diagrams, can we use some synthesis process to generate a good visualization specification? And that's the problem that we are trying to solve in this talk. For the remainder of this presentation, I will talk about some of our preliminary explorations on this project. First, because we are trying to synthesize something, we need to have a synthesizable language in which we can synthesize programs. We need to also talk about how the user would use such a framework. And finally, I will talk about some preliminary ideas on how visualization specifications can be generated from user-provided examples. I will start with the language. We designed a lightweight, constraint-based layout language. Here's its grammar. It's very much inspired by the language that's available in the copy and drag work. I will show you some examples of the visualization specifications written in this language. Here's an example part of the visualization specification. You can say things like, if X is a philosopher, if Y is a fork, if X is using Y, then the shape of X should be laid out near the shape of Y. It refers to the entities in the model. It refers to the relations in the model. And finally, it imposes some geometric constraints between the shapes that are referred to by the other parts of the cross. This is what our language calls a cross. And a visualization specification can consist of multiple crosses that work together to constrain the final layout. There are other more complicated layouts that our language supports, such as how we can cycle the nodes around in counterclockwise or clockwise manner. And the visualizer essentially tries to generate a diagram that satisfies all of these constraints. Because we use pen rules to power the visualization, they are also interactive, allowing people to interact with the generated layout. So that's the language. I will now talk about how we envision how the user would work with, how the user would use our synthesis framework for making their own custom visualizations. I will go through an example of using such a framework. Suppose we are working with a model of a binary tree with some nodes and some left and right children. For example, this instance says we have 3 nodes, and N1 is the left child of N0, and N2 is the left child of N1. The system starts out with nothing, with no knowledge about what our desired layout looks like. So it just randomly places the nodes around. Of course, this visualization does not correspond to how the stakeholders would naturally think of this, this instance. So the user could provide a revision to this diagram because they don't really like it. They could provide a revision that essentially says that whenever there's a left-child relation, it should be rendered as left and below. It should be rendered with a constraint of left and below. And the system figures this out from the user-provided diagram. The system should figure out that the left-child relation should be rendered as left and below. Suppose now we have another instance where this time it only consists of the right-child relation. The system still tries to generate a diagram, but this time it tries to apply the previously generated visualization specification into this new diagram. And because the previously generated visualization specification only talks about left child and our instance has a right child, it's once again being laid out randomly. So the user could rearrange the node to something like this, where the system this time records that the right child relation should be rendered right and below the parent. Of course, it also ensures that the new visualization specification satisfies all the previous instances and diagrams that has been provided to the system. Finally, let's say we have a more complicated instance, this time with both left child and right child relations. the system takes in the latest visualization specification and generates a diagram that satisfies all the constraints. And the user may accept this as a good diagram. So in short, how do users interact with such a framework? Given an instance and a user-generated, user-provided diagram, given an instance and a generated diagram, the user could either choose to accept the diagram, in which case it's added to the example diagram collection. If the user revises the diagram into a new diagram, the new diagram gets added to the example diagram collection. And in each run, the synthesizer takes the example diagrams to synthesize a visualization specification that satisfies all of them. So that's how the user will interact with such a framework. Now, how do we synthesize a visualization specification? I will talk about some of our preliminary ideas. Since a visualization specification is just a collection of clauses, the goal is to compose the appropriate clauses together into a visualization specification. And we can start with a naive and exhaustive approach that essentially searches through all possible clauses up to a certain bound. For each clause, our language allows us to compute a numerical score on how well the example diagram satisfies the clauses. If the score is closer to 1, that means the example diagram satisfies the clauses very well. If they don't, if they are closer to 0, that means that example diagrams violate the clauses. In the end, we just compose the high-scoring clauses into a visualization specification, which by construction should satisfy all user-provided examples. One potential problem is that there are many clauses, many of which have repetitive behaviors. Let me show you an example. If X is a philosopher, if Y is a fork, if X is using Y, then X should be laid out to near the shape of Y. We have another clause here that's essentially equivalent to the previous one, except we switch X and Y around. We can tell that these two are equivalent because they impose equivalent clauses on the same instances. The one might say X is near Y, the other might say Y is near X, but they are equivalent. So the idea is we can potentially use this equivalence to prune out some of the redundant clauses. There are some other cases where some clauses have behaviors that are overlapping with other clauses. For example, this clause only applies the geometric constraint on a specific type of philosophers. So the top clause covers a logic constraint space, and the bottom one, they could use this insight to prune out the bottom one and keep only the top one. In summary, we propose a framework that turns user-provided example diagrams into visualization specifications. I first described the visualization specification language that we are working with. I then showed how the user would use such a tool. And then I briefly talked about some of our considerations on the synthesis algorithm. Some of our ongoing work include exploring ways in which the user interactions can actually inform the synthesis process, by which I mean that if the user revises the diagram from this to that, I think the revisions themselves actually provide valuable information because they indicate that the user does not really like this diagram, but does like that diagram. One potential way of resolving this is to one potential way of using this is to, instead of using only the user-provided examples, we classify them as either positive or negative examples. In the end, we would use both positive and negative examples to synthesize a visualization specification that satisfies all the positive examples and that violates all the negative examples. I will conclude with some quick open questions for discussion. The crucial question is whether or not this tool, this framework, helps stakeholders more effectively create custom visualizations. And this comes with two important sub-questions. The first is whether or not our layout language is expressive enough for the layouts that the stakeholders want. And this, we have to find a balance between expressiveness and generalizability, because if the language is very expressive, we could very easily go into a situation where we are overfitting to a specific diagram example or specific examples that the user have provided. But what we actually want is generalizability on other instances. The second is whether or not this framework actually allows users to efficiently synthesize the visual layouts that they want. And this has to do with essentially how we are planning to evaluate this tool. Can we do some sort of case studies? Can we do some sort of experiments? These are things that we are still exploring. And that's where I will end this presentation. Thank you.
Hey. It's group discussion time. All questions.
Any questions?
Yeah. I'm curious about the kind of end part that you had about positive and negative examples. If I had taken the tree that you showed where it was a correct diagram, and because I'm a little bit nitpicky, pulled the right child up a little bit because I wanted it to be a little bit higher. It feels like making that first one a negative example could be a problem. Have you considered that situation?
Yes, this has been something that Josh, Ansak, and I have been talking about for the last 3 months.
Okay.
We don't exactly have a way of doing this other than if the system cannot find a program that distinguishes between these two, then it just tells the user that you either have to label this as both okay or both not okay. But we could also increase the expressiveness of our language, but I'm wary of that. But yeah, I don't have a very good solution for this. It has been in my mind for the past 3 months. So, yeah, thanks.
Hi, this is great. It's really exciting to see. I'm curious, a lot of the things you were mentioning seem like very general user interface questions for synthesis systems, this kind of process of iteration and cognitive examples. I'm curious to know what you think is unique or special about the domain of diagrams, as opposed to, Flash, doing Excel Flash films.
I feel like diagrams have a lot more diagrams can have a lot more patterns. Like, for example, things that are laid out in a circular or in a clockwise or counterclockwise manner. I feel like that is pretty. That's something that does not really apply to things like flash field, but I'm not exactly sure how what are the differences there are, I guess. But yeah, I feel like diagramming is something that I don't exactly have a very good answer for that.
Could it be potentially more ambiguous than a column of a few months that you provide? There's a famous example of January, February, and then the thing is like March or something. And in the case of diagrams, I mean, the examples were nice in the talk.
Yeah.
In that they are fairly, unambiguous. There was a conveniently omitted, the right branch of the tree. I think in Penrose, if you add another node, the edges start crossing.
Yeah.
And I've been there, and this is not quite ambiguity. So let me just switch to ask this: are there global constraints? Things like edges shouldn't cross. That's not something you say locally. Otherwise, you run into some convoluted blow up of DSL.
I mean, in general, edges should not cross, right? So
yeah, I mean, it's a specific choice you can make as a DSL designer.
Yeah, currently in this iteration of DSL, it doesn't do this. But I was thinking about a DSL version where you can specify that, for example, if you have a left child, you can say that this is on the left of the other thing, and the distance between these two must be at most something like that. We could do that, but it makes the language again more complicated.
And currently, the language doesn't have any bare integers in
Not yet.
Program. Yeah, since the problem will be bad. But yeah.
Hey, so I was curious whether you have considered encoding some of the organization science into your, synthesis process, right? For example, a lot of this has to do with, group organizations, how power dynamics, and all this. And then there's a lot of literature in the organization science and management science that kind of kind of have some, principles as to how you should organize your organization. So one thing that couple of us already comment on was how do you decide whether to take into those examples that you just gave, was it global constraints or local constraints? Is it one instance off? Is it something that you can generalize to all the visualization AI generation? So there's this, organization theory called management by exceptions, right? And you can probably follow some of those theories, see if they can code it in your generation synthesis process as a rule or pattern.
Yeah, I don't think I've heard of that, so I'm definitely looking forward to seeing.
Yeah, we can check it out.
Yeah.
Okay, let's thank Leo. Okay, we have a 15-minute coffee break. If you want to ask questions of Harry or Leo, I assume that they're willing to answer questions during the coffee break. And we'll be back here at 11:10. Please pass your post-it notes, whatever they're called, note cards towards the center. Give to Sarah to give to Leo.
Also, this link should now work for the Zoom.
Yes, okay, that's very important.